Hi there, this is Chem Coach Powers, and welcome to another lecture on the amazing world of chemistry. Today, we're going to be talking about acids and bases. This is always one of my favorite topics, as it is many of my students. So let's get rolling. Let's enjoy this thing. All right, so Chapter 9.1. Our objectives today are to compare and contrast acids and bases, and we'll talk about the traditional properties and the ions that they produce in water. We'll define pH, we'll talk about indicators, and we'll use pH to determine a solution's acidity or alkalinity. All right, so first of all, let's kind of do a basic comparison. Acids are substances that form hydronium ions. So the name hydronium ion just basically is a word that we use, or words that we use to try to indicate this little guy right here, H3O plus. Okay, so we use the word hydronium ion to symbolize H3O plus. What is H3O plus? Well, H3O plus is basically when you take a water and remember there's two extra pairs of electrons over here. And because of those two extra pairs of electrons, sometimes a spare little proton flying through the air happens to get attracted and attaches onto the water molecule. When that happens, because this is an extra proton, right? It's got one little proton in there. Then this whole thing now ends up having a slightly positive charge. Okay, so it's basically saying, yeah, we have H3O now. Okay, and there's a couple little electrons still. And this whole thing has a positive charge. We're writing crooked now. Sorry. All right, so that's hydronium ions. So what is a hydroxide ion? If we look over there at the base, we can see that it says that it's a substance that forms hydroxide ions in water. And a hydroxide ion is basically, believe it or not, here's water, right? Again, same little molecule we were just looking at. And if one of those hydrogens ends up getting pulled away from the water molecule, whoa, go away, okay, then what you end up having is what's left over, which is the hydroxide ion, right? Because it lost a little proton, and that means this whole thing now has a slightly negative charge. Okay, so it's kind of interesting because when you see water itself is continually going through a process of having some of its hydrogens leave one water molecule and attach to another water molecule. So it's basically like we have H2O plus H2O, and in water, this is happening all the time, and we call it the self-ionization of water. This is forming H3O plus and OH negative, because one water molecule is losing a hydrogen and the other water molecule is gaining a hydrogen. So one becomes H3O plus when it gains, and the other becomes OH negative when it loses. And this is going back and forth. So the H3O plus and the OH negative, they're actually going back, and this hydrogen that got jumped on there would actually go back every once in a while and add to another or to another OH ion and become a water molecule. So this is a process that is in equilibrium in water all the time. And when we get into chemistry, we'll learn that the rate at which that is happening has to do with that number there, which is going to have to do with a number that we're going to learn later, has to do with the pH of 7. Anyway, so that's going to be more detail than you're going to need to know right now. But what kind of properties do we have? Well, first of all, what kind of examples do we have of an acid? An acid, you guys are probably familiar with things like citric acid, right? The citric acid is, something that has a sour taste. And so you'll notice that here we have taste sour, right? So if you think about your citrus fruits, they're sour. The reason they're sour is because of the citric acid. And that is one example of an acid. There's lots of different types of acid. If you've ever had vitamin C, Okay. Vitamin C is another type of acid. It's called, somehow that doesn't seem right, but sorbic acid. And that's a very sour tasting thing as well, right? Bases, you're probably familiar with things like soap. And if you've ever had to taste soap, you've probably tasted that it's a little bit bitter, right? And so it's also slippery. Why is soap bitter and slippery? Well, it's because it's a base. Other things that are bases are things like drain cleaner. Now, this stuff is a very strong, powerful base. You don't want to touch that. Okay, that would be dangerous and caustic to your hands. Other things that are acids, we hear about things like hydrochloric acid is a common one we use in the laboratory. And this is used oftentimes in your toilet cleaner. Okay, so we can see that there are certain types of cleaners that use acids and bases to clean things as well. Okay, the other thing we want to talk about here is that acids are good electrolytes and so are bases. These are both allowing for electricity to conduct. If they get dissolved in water, they turn into ions, and those ions allow for electricity to conduct. And so acids and bases are both electrolytes. And then there's an indicator paper called litmus paper, and acids will turn the litmus paper red, and bases will turn the litmus paper blue. So just think base blue, B and B, right? The B of blue for base, okay? That is one way to remember that bases turn litmus blue. All right, so this is an example of nitric acid, which is a strong acid, being a strong electrolyte. You can see how this light bulb here is really well lit up. We're going to show you a picture in the next one where it's not as well lit up. Remember, electrolyte is a substance that dissolves in water to give a solution that conducts an electric current. And so if I take plain water, which actually does not conduct electricity very well at all, pure water has very few ions in it. If it's completely pure and doesn't have any minerals in it, it will not conduct electricity very well at all. This light bulb wouldn't be lit up at all. But if I put a little bit of nitric acid in it, it's going to suddenly allow the light bulb to conduct electricity. Why? It's because all of those little ions of the nitric acid have separated out, and so now it allows for electricity to move back and forth between those electrodes. Well, that's a strong acid. A weak acid like vinegar, okay, so this is a weak acid. The last one, nitric acid, was a strong acid. The weak acid actually is a weak electrolyte. And we're going to talk about what the differences between strong and weak acids are here in just a second. But you'll notice that the light bulb here is not very well lit up. There's a little bit of light there. You might not see it too well, but there's a little bit of light there. And that's because it is forming some ions. And the ions that it forms, it's forming some of these hydronium ions down here and then some of these acetate ions. Acetic acid is basically vinegar, and it's made from acetate ions. Okay, so you're going to see that weak electrolytes are, weak acids are weak electrolytes, and they don't conduct electricity very well. Now, if you get a whole lot and you get a high concentration of weak acid, then it will conduct electricity better than what you see there. But equal amounts of strong acid and weak acid are going to give you different amounts of conductivity. So let's look at an example. Let's look at nitric acid and what's going to happen to it, and we'll compare that to acetic acid. Notice how in the nitric acid we have an arrow that just points in one direction. And what we're trying to show here is that there's complete dissociation, that when you have this nitric acid, that extra little hydrogen is going to leave, and it's going to go onto the water, okay? And now it forms this hydronium ion. But it doesn't want to go back. This arrow is pointing in one direction because it doesn't like to reverse. We talked about equilibrium before, how the arrows can go both directions. It doesn't like to reverse. And so this nitric acid tends to go in one direction, and it's going to form this hydronium ion and the nitrate ion, and it doesn't reverse. And so this is a strong acid because it completely dissociates. Now, acetic acid, on the other hand, acetic acid is a weak acid. So some of the hydrogens are going to come off, okay? And you'll notice that there's a hydrogen that leaves. It's this one right over here. You notice that it's not over here on this side. And that hydrogen is going to go to water, and it's going to form this hydronium ion. But you'll notice that we have arrows pointing in both directions this time. And what that means is that it is going back and forth, okay? And so this reaches equilibrium. And not only does it reach equilibrium, but not all of these particles, these acetate ions, are going to come apart like you have with a nitric acid. And so over here with a strong acid, you have complete dissociation, okay, or ionization. Dissociation. Okay, the process is actually called ionization with molecular compounds, but we're just going to call it dissociation, meaning that they're coming apart, okay? And with acetic acid, you don't have complete dissociation. You have partial dissociation. And again, you're going to reach this equilibrium where you have these arrows pointing in both directions, but you don't have all of the particles coming apart. And that's the big difference between a strong acid and a weak acid, okay, is that you're going to end up having a different amount of the particles coming apart. If all of the particles are coming apart or all of them are coming apart, then we call it a strong electrolyte or a strong acid in this case. And if just some of them are coming apart, it's a weak acid or a weak base or a weak electrolyte in this case. All right, so that's what we're talking about here. And again, you saw me talking about the word dissociation. Dissociation in chemistry, you're going to learn, is actually associated specifically for ionic compounds. These are both molecular compounds, and so we actually use the term ionize. That's the correct term to use for molecular compounds. But dissociate kind of makes more sense, I think, in a lot of people's minds because it's coming apart, right? So strong acids completely ionized, weak acids only partially ionized. Now, it's important to remember that strong and weak don't have anything to do with concentration. They are not related to concentration. So you can actually have a really concentrated weak acid that could actually be more dangerous than a really diluted strong acid. And so know that those two things are not necessarily related to each other, right? So strong acids can be really dangerous and caustic, but if they're really diluted, if there's very, very little of it in a big solution of water, then it's really not going to do you much damage at all. Whereas a weak acid, which wouldn't normally, like, think about vinegar, right? It's not really going to normally be a big problem to, touch. And yet, if you have really concentrated acetic acid, it could actually be dangerous to you, okay? All right, so here are some common acids. You heard me talk about hydrochloric acid already, and that's a strong acid. You've seen now, we've talked about nitric acid, which is also strong. You should also know that sulfuric acid is strong. And then you should know that acetic acid is weak, and then citric acid is weak. We don't really talk about formic acid too much, but formic acid is the stuff that ants have when they take a bite out of you and it hurts. It's formic acid. And so it's not like these things are not caustic and not dangerous. They can actually be dangerous in high enough concentrations, right? Formic acid is also something, yeah. All right, so let's go on to bases. So let's look at what happens when we form a base. Here I have sodium hydroxide, and it's gonna split apart into the sodium ion and the hydroxide ion. So a base is something that's going to form hydroxide ions in solution. So when I put sodium hydroxide in water, it's gonna make these two little ion solutions. I'm gonna put AQ here to show that it's in water. Those separate and split apart. Now, because I'm showing just the arrow in one direction here, you can probably indicate that this is a strong base, right? Whereas over here, I have ammonia going in water, and you'll notice that we have two arrows. The arrows are going in both directions, and I do form the ammonium ion, and I do form hydroxide. Okay, what's happening there? You're like, how does it form that? Well, remember, this is H2O, and then this is NH3, and if we do the Lewis structures of these, we can see that this nitrogen has a couple extra electrons. And so what happens is that this hydrogen will go and just kind of get a little free ride every once in a while from the electrons on that nitrogen, and it just kind of attracts to those. And so then it kind of breaks this bond for a moment. And so this is, again, an ionization process. And you'll notice that the arrows, again, are going in both directions. And so every once in a while, that hydrogen will come back off of that and come back over here and join back up with the water. Okay, so this is a weak base because not all of the ammonia is coming apart and forming hydroxide ions. Okay, so let's look at some strong bases. Potassium hydroxide is strong. We can see that it's used in manufacturing soap, dyeing products. Sodium hydroxide is also strong. Again, it's used in making soaps and in making petroleums and cleaning drains. The sodium hydroxide is the stuff that you'll have inside like your drain cleaners. It's lye. Calcium hydroxide also strong. And this is going to be used for, mortar, plaster, cement processes, treating lakes. And then you have our weak bases, okay? Our ammonia, our methylamine, and our aniline. Ammonia is really the one you want to probably focus in on. That's going to be used to, make fertilizer and cleaning solutions. You can see the glass cleaner here. That actually is a weak base. That's made up of ammonia. Milk of magnesia. This is magnesium hydroxide. Okay, notice that all of these things are going to be turning litmus paper blue. So the paper is pink as it starts, and it turns blue once it has been exposed to the base. Okay, methylamine and aniline, not too important to know, not stuff that we typically deal with on a day-to-day basis. So indicators are chemicals that are used to tell us whether or not something might be an acid or a base. The indicator will actually change color based upon its exposure to a particular pH level. Okay. Red cabbage juice is just a fascinating and super fun natural indicator. Notice if I take some red cabbage juice and I blend it up in a blender and I take the water off of it, then I can actually get this huge array of colors that you see in all these little test tubes that go from something that's pretty acidic to something that's pretty basic. And these numbers that you see down here, these are the different pH numbers. We're going to talk about that here in a second. But this is the different range of colors that you can get from the red cabbage, or sometimes you're used to seeing that. Maybe you might call it purple cabbage. But that's the actual natural color indicators of different pHs from red cabbage. Now, when you see an indicator like a litmus paper or something like that, basically the concept is pretty much the same. With litmus paper, you're just dealing with a chemical that will just change from one color to the next, and it doesn't have this variety. But when you look at pH paper can actually have a whole realm of different colors that it changes based upon the pH of the solution that you put it into. And what happens is they take this pH paper. It's basically a regular piece of paper that they coat with a bunch of different types of chemicals that are going to change different colors based upon the different pHs that they're exposed to. And they're all a mix of chemicals that are compatible with each other so that they make a nice little blend of colors. And so this is what you see with the pH paper. And again, I want to point out that the things that are really acidic, okay, battery acid, really acidic, pH is 0. Okay, so the lower the number, this almost seems counterintuitive, but the lower the pH value, the more acidic it is. And then over here, my pH of 14, which is a high number in pH, that's just something that's very, very basic, right? That's a really strong base. So the number here, number 7, I told you we would talk about that in chemistry later on, but that number is basically saying you have an equal number of hydronium and hydroxide ions, and that's 1 times 10 to the 7th within a mole. And so anything where you get more hydroxide ions, your pH is going to go toward the number of 14. If I get more hydronium ions, then my pH is going toward the number of 0. And the reason that those numbers are that way, you'll learn in chemistry, okay? But just kind of remember, it's kind of counterintuitive. But pH is a measure of the concentration of the hydronium ions, or the H3O plus ions, right, that are in solution. All right, so let's look a little bit more at pH, because pH is related to that hydroxide ion concentration, right? So the pH actually comes from French when they first started talking about that. And it was the power of hydrogen. Okay, poder de hydrogen. Not that I know anything about French, but I know that at least I remember at one point it used to be in French. I think it's actually poder. No, it's in Spanish. It's poder. Yeah, I don't even remember what it is in French anymore. Anyway, so the power of hydrogen and the hydroxide ion concentration is going to be affected by the hydronium ion concentration. Okay, so how are they related? Well, the concentration of hydronium ions is related to the concentration of hydroxide ions because basically as one goes up, the other goes down, right? As I'm taking water and I'm making more hydroniums, then there's going to be a relationship between those two values. And so the more hydroxide ions I have, that's going to change my number. So the pH of a solution can actually be used to calculate the hydroxide ion concentrations. You're not going to have to worry about how to do that in this class. You'll do that in chemistry, but don't worry about that right now. But we use pH to express acidity or basicity. And again, like I said, it's kind of counterintuitive, but a pH of 1 or 0 is high acidity, a pH of 14 is low acidity. And it's actually kind of interesting because you can actually get pHs that are in the negatives. You're not going to see that here on your class. You're going to just go down to 0. That's the lowest pH. But the lowest pH known of any solution is negative 33. So you can actually get very, very low pHs. And it just means that your concentration of hydronium ions per mole is really high. Okay. All right. So a couple other things about pH. Remember that pH needs to be determined. And again, this is maybe a little bit more in the chemistry world, but it needs to be determined from a strong acid. Weak acids, because they don't completely dissociate, you can't really, calculate pHs from weak acids directly. Okay, so when we calculate pHs, we want to use a strong acid to figure out what that pH is. Then we can use that strong acid and we can calculate something from a weak acid. But we need the strong acid to calculate pH. And again, this is a mathematical function. Remember, I told you there was something about 1 times 10 to the negative 7th. Well, that negative 7 right there, that 7 that you see right there, actually is where we get that 7 right there. And so if I'm talking about 1 times 10 to the negative 14th moles per liter, then that's going to be a pH of 14, which basically means I don't have as many hydronium ions, right? Because it's times 10 to the negative 14th per mole. Remember, a mole is times 10 to the 23rd. And so I actually have fewer hydronium ions when I have 1 times 10 to the negative 14th, right? Because times 10 to the negative 14th is a smaller number than times 10 to the negative first, for instance. Anyway, so concentration of hydronium ions in a solution of strong acid is the same as the concentration of the acid. So when we talk about concentration of hydronium ions, you can correlate that with the concentration of the acid. All right, a couple other things that we want to finish off with here. Remember that small differences in pH are large differences in acidity. It's a factor of 10. Okay, so every time we increase our pH by 1, we're increasing by a factor of 10. It's a logarithmic scale. And so something that's a pH of 5 and a pH of 3 have 100 times difference with each other. Okay, so apple juice is going to be 100 times more acidic than coffee because it has a pH that is 2 values, but each value is 10 times that, right? So it's going to be 10 times 10, which is 100. You can also measure pH with electronic pH meters. And this is something that is better at measuring the pH than indicators. And they work based upon the electrolyte capacity or the electrolyte ability, the ability to conduct electricity, right? So as you get strong concentration of a strong electrolyte, then you're going to have more electricity conducted. And so pH meters actually work on the concept of how well does it conduct electricity, and I can tell you what the pH is based upon how well it conducts electricity. And so that's what's happening here. You can see a pH meter giving a value of 4 for the tomato juice that they're showing. And so is that mixture acidic or basic? Acidic, right? Because it's a pH less than 7. 7 is considered neutral. Anything below 7 is acidic, and anything above 7 is basic. All right, so we've learned some good stuff today on acids and bases. So let's see if we can compare and contrast acids and bases using traditional properties. Yeah, traditional properties, things like acids are sour, but bases are bitter. Acids turn blue litmus paper red, bases turn red litmus paper blue. The ions, bases are creating hydroxide ions and acids are creating hydronium ions. Now, you learn in chemistry there's different ways to do that definition now, but that's an old school way, and we still are keeping you with that old school way for right now. And the next objective, define pH, use it to determine the solution's acidity or alkalinity. pH is the power of hydrogen, right? How much of the hydronium ions do we have? The concentration of the hydronium ions in a solution. And the more hydronium ions you have, the more acidic it is. And again, we use that concentration to come up with that number. So 10 to the negative 7th is going to be a 7. 10 to the negative 3rd would be a 3, things like that. All right, so you guys have learned some good things today. Know a lot more about acids and bases than you did when you started, and you are now ready to tackle this on a test, I hope. All right. Please ask me if you have any questions. I am always here for you. You guys be kind to one another. God bless you. Have a great day.